Alrighty folks, so what I'm going to do in this video is work through that hand rule practice quiz that I've posted, and I'll kind of do it here with my hands, kind of first person view, so you can actually see how I would use the hand rules here. So you can kind of treat this as a tutorial for the hand rules if you're having a tough time with them at all, or you want to see me demonstrate them, okay? And you can also use it if you're stuck on a specific hand rule practice quiz. It can be for the practice quiz as well. I'll just say right at the beginning here, okay, if you go to the description of this video, if you're looking at it on YouTube, like if you're looking for a specific question in this quiz, in that description, you'll find timestamps. If you click on them, they'll take you directly to that question, so you don't have to search around in the video for the specific one you're looking for. All right, so this first one here, it says the diagram shows a conductor between a pair of magnets. The conventional current in the conductor flows out of the page, so they're representing that with a dot there. What is the direction of the magnetic force felt by the conductor? Okay, so we know when doing a hand rule, the first decision we basically have to make is it one of the first two, like this, or is it one of the third hand rules where we've got our fingers like this? Okay, and that comes down to, again, the first two hand rules are for when a charge is moving and producing a magnetic field. And we want to know about that charge's magnetic field, or we're interested in that situation, right? The third hand rules are for when a charge is moving through an external magnetic field, a magnetic field it is not creating, and as a result feels a force. So this is definitely a job for the third hand rule in this case, right? We have a charge, conventional current moving through an external magnetic field that it had nothing to do with creating, and as a result, it will feel a magnetic force. So with that in mind, if we're thinking about conventional current, we know that conventional current is the direction a positive charge would flow, right? So does that mean I want my right hand or my left hand? To think about current, which is positive, we use right hand. Okay, so now let's look at how we would orient our hand. We want the conventional current, so the charge motion, that's going to be our thumb, that needs to be coming towards us. Now the fingers, those are the magnetic field. We know magnetic field, the external magnetic field, we all know it leaves north, enters south, right? It's the direction a north pole would point its compass if you put it there. So in this case, the magnetic field, the external magnetic field that the current is flowing through would be towards the top of the page. So the charge, the thumb is coming towards us, external magnetic field is towards the top of the page, and then our palm, I think of it as it like pushes like a force. So it looks like in this case, it would be pushing, my palm is left pushing towards the left side of the page when I take my right thumb and point it towards me, and my right fingers and point them towards the top of the screen. So that's making me think towards the left side of the page. With most hand rule problems, there's a nice little way to check your work. You can use the other hand and see if you get a consistent result, right? So if we were thinking about electron flow, how a negative charge would move, well, it would do the opposite of current, right, which is positive. So electron flow, if I use my left thumb, that would be into the page, but the magnetic field would still be towards the top of the page, and sure enough, confirming my answer, this should feel a force towards the left side of the page, right? My left palm points to the left side of the page. Okay, so we've got that a current in the wire shown below is flowing to the left of the page. So current to the left. In what direction will the wire feel a deflecting force? Well, we can see here we've got dots for an external magnetic field that this current is flowing through, right? So again, first two hand rules are for when you have charge moving and you're interested in the magnetic field that moving charge itself is creating. The third hand rule is for when a charge is moving through an external magnetic field and finding the force that results from that situation. So in this case, we definitely need to use our third hand rule, okay? Now, current, again, is defined as how a positive charge would move. So I'll use my right hand for positive charge. Left would be for negative. So current is moving to the right side of the page. So I'm going to take my right thumb and point it towards current is moving to the left side of the page. So I'll take my right thumb, point it to the left side of the page, matching the current there. Okay, and now the magnetic field is dots, which means it's coming towards us. So the magnetic field that it's moving through is out of the page towards us. So we want our fingers pointed back at us, thumb to the right side of the page, and we can see that our palm, which shows the magnetic force, is pushing up towards the top side of the page. Okay, so I would say towards top of page. We can always double check our work by using the other hand and making sure we get a result that's consistent. So left hand is for thinking about what negatives are doing. If positive current is flowing to the left, then negative electron flow would be flowing the opposite direction to the right, right? But the external magnetic field is still out of the page towards us. And so if I do it with my left hand, sure enough, I get a consistent result. This wire would feel a force, a magnetic force, pushing it toward the top of the page. So determine the direction that the charge, if it is an electron, so it's negative, right away thinking left hand, will initially feel a magnetic force once it enters the magnetic field shown below. Okay, so we have a moving charge entering an external magnetic field that it's not creating, right? It is creating its own magnetic field, but it's entering another magnetic field that it had nothing to do with. And as a result, it will feel a force perpendicular to its direction of travel and its own magnetic field and this magnetic field. Okay, so with that in mind, we want our third hand rule, right? That tells us about the force, and we want to use our left hand here. So a negative electron is moving towards the left side of the page, so left thumb towards the right, the negative electron is moving towards the right side of the page. It's coming from the left is what I meant to say. So point my thumb in the direction the negative charge is moving, and now the external magnetic field it's entering, that's our fingers, is pointed towards the bottom of the page. So charge is moving this way, external magnetic field it enters is towards the bottom of the page, and our palm, I think of it as like it pushes like a force, right? That's a good way to remember it. So the palm is pushing out of the page towards us. So this electron would feel a force towards us, out of the page. Determine the direction of the resulting magnetic force. Okay, so already I'm thinking it's got to be the third hand rule, right? That's the only one with a force, and it's for when a moving charge enters an external magnetic field that it did not create, and as a result, it feels a force from the interaction with its own magnetic field. So the current in the wire is directed into the page as shown. So we've got current, so let's use our right hand rule. Current is flowing into the page, so we're going to take our right thumb and point it into the page, but then the external magnetic field, which is our fingers, is directed towards the top of the page. So we need to take our right thumb, point it into the page, and then take our fingers and put them towards the top of the page, and whatever direction our palm is left pointing is the direction of the force this wire will feel. So when I do that, I'm getting it towards the right side of the page, right? The nice one about this is you can kind of imagine pushing with your palm, like a force pushes. So doing that, the right side of the page, and as always, we can kind of check our work by seeing if we do, the opposite charge motion with a negative, do we get a consistent result? So if current positives were flowing into the page, well, negatives in the wire we would think of as flowing out of the page, right? Coming towards us. So if I take my left thumb now and point it towards me, take my left fingers and point them in the direction of the external magnetic field, sure enough, same result, a force towards the right side of the page. All right, so I've got a beam that contains positively and negatively charged particles right here, enters a magnetic field, so an external magnetic field, so we're thinking third hand rule, a charged particle enters a magnetic field that it did not create and feels a force as a result. So which of the following statements is true? Beam 1 is positive, beam 2 is negative, 1 is negative, 2 is positive, both negative, or it's impossible to say. Okay, well, right away I'm thinking they can't both be the same because they deflected in opposite directions, right? So really this just comes down to use your third hand rule, and if the left hand explains one of the beam's motions, that beam must be negative. If the right hand explains one of the beam's motions, that beam must be positive. So they both came in moving to the right. Let's try left first. So we've got a magnetic field, they're showing X's. That means the external magnetic field is into the page. So I'm going to put my fingers into the page and my left thumb towards the right of the screen. I get a magnetic force, my palm, pushing down towards the bottom of the screen. So what would that do? It would cause this velocity to, well, bend downwards. And then that would change the force to be in. That's how we get circular motion from moving charges in an external magnetic field, right? So which of the two paths does that explain? Looks like it explains charge 2's path, or beam 2's path. So I'm thinking beam 2 is negative, okay? Now, if we try this with the right hand, let me take my right thumb and point it towards the right side of the screen. Fingers still into the page. It's not like the external magnetic field has changed its direction. Sure enough, I get a palm facing towards the top of the screen. So these are going to feel a magnetic force upwards towards the top of the page. So that's why path 1 deflected that way. So it looks like path 1 was explained with the right hand, 2 with the left hand. So 1 must be made of positive charged particles, 2 must contain negative. So this one. All right, so a negative charge enters the electric field shown below horizontally from the left. If you were going to add a magnetic field that would cause the charge to not be deflected, what orientation would it need to have? Okay, so we've got an electric field here. A negative charge is definitely going to be deflected if it enters this field, right? I mean, a negative is going to be attracted upwards to this positive plate. It's going to be repelled by this negative plate. Or we could even just say, we know that electric field direction is defined as the direction in which a positive test charge would feel a force. So a negative test charge would feel a force in the opposite direction as that electric field. No matter how you think about it, you get that in a negative charge, if it comes in like this, is going to be deflected in a parabolic path up towards the positive plate. Okay, so with that in mind, our question is, how do we stop that? How do we introduce a magnetic force to stop that? And what direction would the magnetic field need to be in order to provide that magnetic force? Well, again, the charge is going to feel an electric force upwards. So we need a magnetic force downwards in order to cancel that upwards electric force out and cause it to not deflect, right? Otherwise it will deflect. So right away we know we need to take, it's negative, so we need to take our left palm and point it downwards so that the magnetic force on the charge is downwards to cancel out that upwards electric force, right? So palm needs to be down. Now our negative charge is moving towards it enters from the left, so that means it's moving towards the right. So we know that negative charge is moving towards the right. We know our palm needs to be facing down to cancel out that electric force that's up. And so where are our fingers left pointing? Because that is the direction of the external magnetic field we would need to produce this downward force. Well, into the page, right? So to get a magnetic force towards the bottom of the page, to cancel out that electric force that's towards the top of the page, if our charge is moving to the right, we need a magnetic field that is into the page. All right, so the blue arrow represents electron flow. Electrons are negative, so I'm thinking left hand already, through a conductor toward the bottom of the page. The orange circles show an external magnetic field. Okay, so we're not using one of our first two hand rules probably, where we're thinking about a charge is moving, what magnetic field does it create? We're thinking about third hand rule, charge enters an external magnetic field it had nothing to do with creating, and as a result of doing that, it feels a force. Okay, directed out of the page, so dots show that the magnetic field is out of the page. Determine the direction of the resulting magnetic force. All right, so yes, third hand rule, that's the only one with a force from our palm. So left thumb needs to go towards the bottom of the page because that's the way electrons are flowing. And then our left fingers, which would represent the external magnetic field, need to be pointed out of the page towards us. So that means our left fingers are coming towards us, left thumb towards the bottom of the page, and I get that the palm, right, pushing like a force would be towards the right side of the page. Okay, we can always double check by using the right hand and thinking about what a positive would do in this situation. Well, if negatives are flowing down towards the bottom of the page, we know that positives would do the opposite. So let's just quickly double check. Take my right thumb, point it towards the top of the page, fingers towards us because that's still the direction of the magnetic field. And sure enough, they would feel a force towards the right side of the page. So the wire in either case would be pushed to the right side of the page. Okay, so we're asked which direction will the conducting loop turn as viewed from the same perspective as the picture. Note that the positive terminal of the battery is closer to us, the negative is further from us. They are labeled, but it's kind of hard to see. We want to figure out which way this will turn. Well, first let's ask ourselves, why will it turn in the first place? Well, because charge is moving through this wire, right? And it's doing so through an external magnetic field. We know that as a result, it will feel a force, right? And that force is going to be what causes the wire itself to turn. So if we can think about what direction the force is on the wire in certain locations, we can figure out which way those forces would cause it to spin. So let's go ahead, let's think about positives first, but we know we can always confirm later with a negative and make sure we get a consistent result. What's a positive charge going to do? Well, it would leave the positive terminal, right? Head this way. So in this section here, it's kind of headed away from us into the page, right? So let's take our right thumb for positives and point it into the page here, okay, for that section of the wire. And then the magnetic field, the external magnetic field, we know magnetic field always leaves north, enters south. So these positive charges are moving through an external magnetic field created by these magnets, and that magnetic field is towards the left side of our page, which is our fingers. So like we said, for that section of the wire, right thumb into the page, magnetic field towards the left side of the page that it's moving through, and we get that our palm is facing upwards. So the force would be pushing towards the top of the page for this section of the wire right here. Now, what does that mean for rotation? We can already kind of start to think about it. If that left section there is feeling pushed towards the top of the page, it's kind of going to cause a rotation like this, right? We can start to think about that already. So that would be clockwise, okay? But we can keep going and think about, confirm this, because those positives aren't going to stop there, right? They're going to keep going. They're going to keep going. They're going to loop through here, and then they're going to come back towards us through this section of the wire. So let's think about the force that that section of the wire is feeling. So like we said, as they make that return journey, right, here back towards the negative terminal eventually, they're now coming towards us. Now the external magnetic field direction hasn't changed. It still leaves north, enters south. So fingers still towards the right side of the page. Palm therefore pushing down towards the bottom of the page for this section of the wire here. Charge comes towards us, fingers that way, downwards. So let's think about that. This section of the wire we said was feeling a force up. This section of the wire we said was feeling a force down. So what's going to be the effect of that in terms of rotation, right? If you push this up and this down, it's going to rotate like this, the way a clock rotates, right? 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock. So it's rotating clockwise. Let's quickly confirm by using our left hand and thinking about a negative charge, make sure we get a consistent result. A negative charge is going to leave this negative terminal, head through this section of the wire. So now a negative charge here would be going away from us. But the external magnetic field's still the same, leaves north, enters south. So with our left hand, if we point our left thumb into the page to think about this section of the wire here, fingers still towards the left side of the page, sure enough, we get a force down towards the bottom of the page for that section of the wire there, okay? So like we said with the positive, same result. So that's gonna feel pushed down. Then the negatives will come around this way, and then they'll be headed towards us, towards the positive terminal for this section of the wire here. So if a negative charge is coming towards us, but the magnetic field is still towards the left side of the page, sure enough, palm points up. It's feeling a force up over here. So it's the exact same thing we got with our right hand in thinking about positives when we use our left hand and think about negatives. Up over here, down over here, clockwise rotation.